Humiliated at the end of World War I by the Versailles Peace Treaty, Germany had risen again, this time with a vengeance.
As ruas da estação até à chancelaria do Reich transformaram-se em verdadeiros tapetes de flores.
The Versailles Peace Treaty had forbidden weapons like tanks, planes, heavy artillery to Germany. But nobody had thought of mentioning missiles.
A young Nazi scientist, Werner von Braun, had developed the first controlled unmanned missile, the V-2, and it was used to create havoc in World War II and all over Britain. But as we know, Germany lost the war, but the science and the scientists didn't go to waste. They were all put to use.
Explain to people that don't know what we're talking about. Operation Paperclip was when, after World War II, the United States gathered up a ton of scientists from Nazi Germany, brought them over to America, and even Werner von Braun. They had Werner von Braun run NASA. He was a Nazi.
The Americans and the Russians fought for technological supremacy throughout the Cold War, and the missiles played a core part in them. With integration with nuclear warheads, they could not stop anymore, and all they did was innovate more and more and more. One must expect the development of weapons to go down and peace to go up. The development of missiles never went down. In fact, they only sped up. And even today, they are being continually improved with more and more and more sophisticated technologies. This is missile technology. Our topic today is subsystems of missile. Our team consists of Mustafa, Deepika, Harush, and myself, Vedram. The outline of the presentation is as follows. We begin with an introduction. We go to talk about the missile guidance system, line of sight system, proportional navigation, warheads, ballistic missiles, and missile propulsion. A missile is defined as an object which is forcibly propelled at a target, either by hand or from a mechanical weapon. They were developed at the end of World War II when technologies were evolving and people were looking for unmanned systems to attack the enemy. Missiles are engineering feats and they have best multidisciplinary integration between branches of mechanical, chemistry, aerodynamics, electronics, and computers. The body of the missile is designed to be aerodynamic so as to efficiently reach from the place where it starts to its destination where it detonates. and it has to do so by using minimal amount of fuel, and it has to make sure that it kills a large number of people per use, which and that may vary depending on the mission scenario. Now, a missile has many parts, but if we go from top to bottom, the first part on the top is known as the warhead. The warhead is what contains the explosive in the missile. As we go down, we get the body of the missile, which contains the fuels, which we will talk about later. And below that is the engine or the motor, which is what is the reason for the thrust. The control systems and the guidance systems is controlled by flaps called ailerons that will also be spoken about as we go. We will be reviewing subsystems such as the guidance systems, the propulsion systems, and a few algorithms for the operation of the missile. The first thing that we will view is the missile guidance system. The missile guidance system consists of three main parts. One is, of course, the navigation, such that it has to reach the destination from where it starts, and the path it takes relies on the guidance. And sometimes we may have to change this path, and for that we have control systems. Now, there are a few types of guiding systems: command guidance, homing or seeker guidance, beam rider guidance, and inertial guidance. I will talk in brief about all these four types of guidances. In command guidances, the guidance signal is sent from the launch site to the missile, that is from the launch station. This is done because the target may be changing their location, and its whereabouts can be only known to the command base, and it cannot be similarly followed by an algorithm on the missile. At frequent intervals, the missile's deviation from the target to launch line of sight is estimated on the ground, and new orders are subsequently sent to the missile. The immediate positions of the missiles and the target are discovered to calculate errors. And these use systems such as radios and radars and lidars, sonars also sometimes, and it can also use temperature sensors. It can also be integrated with satellites. The next type of guidance system that we'll be talking about is the homer or seeker guidance, which is usually employed by short-range missiles. The missile picks up signals by itself from the target. For example, we have heat-seeking missiles, where missiles, suppose there's a missile that needs to hit an aeroplane, it focuses on a region of high temperature, which is the engine, and if the plane tries to change its course of path, the missile also changes its path towards the temperature. The next type of guidance is the beam rider guidance, and in this technique, the guidance system will use a radar antenna to direct a beam of energy at the target, illuminating it, and it will hence follow it. And the most obvious form of guidance is called the inertial guidance, in which the missile is oriented to launch at a certain orientation, and it will reach the destination without any control in between using ballistics. The most common type of missile, that is the ballistic missile, uses this inertial guidance, where after launch the only things that control the path of the missile is gravity and air resistance. The next thing we're going to talk about is a simple line of sight system, where, as it speaks for itself, there are three components. There is the base station, the missile, and the target. And the missile takes the path that the command of the line of sight of the command station and the target. These three things align such that the target is hit. The next thing that we're going to talk about is proportional navigation. This is also a method of hitting the target, where a missile is launched, and it's launched in such a way that again, this comes under the initial guidance system. It is pre-calculated. The missile launch is pre-calculated such that the missile reaches a place where the target will be in some time, and the path it follows after a point will maintain a constant slope with the target. It relies on the fact that the two objects are bound to collide if their direct line of sight does not change as the range closes. In proportional navigation system, the missile stays on trajectory with a constant bearing angle to the target. Now, Harush will continue and we'll talk about missile warheads.
So I'm Harush, and as mentioned in the slide, warheads are the explosive chemicals which are delivered by a missile. So, missile being a destructive weapon, its main aim is to detonate and discharge the warhead such that it eliminates the enemy or the target. So, each type of target is subjected to different physical destruction intensities. So, the same warhead can't be used for all kinds of targets. We need to make sure that there is maximum impact in the attack made by the missile, and also make sure that the warhead used is cost effective. The types of warheads include explosive, conventional, blast, fragmentation, nuclear, chemical, and biological. The different parts of a warhead are fuse, the fuse, explosive chemicals, and the warhead case. The warhead case is basically the protection around which inside which the chemicals are placed, and fuse is the essential part. It's such that it activates the warhead mechanism when the missile is in the vicinity of the target. It also maintains the warhead in a safe condition during all the initial phases before the discharge. So it basically includes different kinds of sensors which gets activated as the missile gets closer to the target. Okay. So in this slide, we're speaking about the ballistic missiles. They are the ones which use projectile motion to deliver warheads on a target. These missiles are guided only during a brief period of their trajectory and not during their entire trajectory. So most of its flight is unpowered in this case. A ballistic trajectory includes three phases, that is boost phase, mid-course phase, and terminal phase. So the mid-course phase is the phase during which the warhead is discharged from the ballistic missile. This missile is launched directly into the high layers of Earth's atmosphere initially. It travels outside the Earth's atmosphere, and this is when the warhead is discharged. And this warhead falls back to the Earth's surface, such that gravity plays a major role in this case. The warhead comes down to the Earth's surface where it hits the target and it eliminates the target. Yeah. Mustafa is going to continue now.
So I'm Mustafa, and now I'll be talking about missile propulsion. So whenever we need a missile to be launched and to actually go hit its target, it has to first be launched and sent into its path towards the target. For that, we need propulsion, which is usually carried out by a rocket, from which the missile is then ejected. So talking about the basic physics of the propulsion, it's nothing but Newton's third law of motion being followed, and principle of conservation of momentum is in action. Here we can see the simple derivation for the expression for thrust of rocket. It's u times r, where u is the velocity of exhaust relative to the rocket, and r is rate of mass ejection. And here the negative sign indicates that motion is in opposite direction. Coming to propulsion systems, there are solid, liquid, hybrid, and solid liquid hybrid propulsion. There's gas turbine engine and ramjets. Talking about solid propellants, they're composed of mixture of granules of solid oxidizers such as ammonium nitrate, ammonium dinitramide, or potassium nitrate in a polymer binding agent with flakes or powders of energetic compounds like RDX or HMX. Sometimes burn rate modifiers are like iron oxide are also added. So talking about the advantages and disadvantages of solid propellants. Solid propellant rockets are much easier to store and handle than liquid propellant rockets. High propellant density makes for compact size as well. These features plus simplicity and low cost make them ideal for military and space applications. Their simplicity also makes solid rockets a good choice whenever large amounts of thrust are needed and cost is an issue. The space shuttle and many other orbital launch vehicles also use solid fuel rockets. A disadvantage that it has a lower specific impulse, which is a measure of propellant efficiency when compared to liquid rockets. As a result, the overall performance of solid in upper stages is less than liquid. Now, talking about liquid propellants, the main type of liquid propellants are storable propellants, which tend to be hypergolic or cryogenic. Uh, Liquid fuel rockets have higher specific impulse than solid rockets and are capable of being throttled or shut down or restarted. Cooling can be done regeneratively with liquid propellants. The primary specific impulse advantage of liquid propellants is due to the availability of high performance oxidizers like liquid oxygen, dinitrogen tetroxide, and hydrogen peroxide, which are available and have better specific impulse than ammonium perchlorate, which is used in most solid rockets. The main difficulty with liquid propellants is also with the oxidizers. Storable oxidizers such as nitric acid and nitrogen tetroxide tend to be extremely toxic and highly reactive, while cryogenic propellants, by definition, must be stored at low temperature and can also have reactivity or toxicity issue. Liquid oxygen, also known as LOX, is the only flown cryogenic oxidizer. Others, such as FLOX or LOX mix, have never been flown due to instability, toxicity, and explosivity. Now, talking about hybrid propellants, hybrid propellants have a storable oxidizer used with solid fuel, which retains most virtues of both liquids and solids. The fluid oxidizer can make it possible to throttle and restart the motor just like a liquid fuel rocket. Hybrid rockets can also be environmentally safer than solid rockets since some high performance phase oxidizers contain chlorine versus the more benign liquid oxygen or nitrous oxide often used in hybrids. This is only true for specific hybrid systems. There have been hybrids which have used chlorine or fluorine compounds as oxidizers and hazardous materials such as beryllium compounds. Because just one constituent is a fluid, hybrids can be simpler than liquid rockets depending motive force used to transport the fluid into combustion chamber. Hybrid motors suffer two major drawbacks. The first, same as solid rocket propellants, is that the casing around the fuel grade must be built to withstand full combustion pressure and often extreme temperatures as well. However, modern composite structures handle this problem very well. And when used with nitrous oxide and solid rubber propellant, a relatively small percentage of fuel is needed anyway, so the combustion chamber is not especially large. Talking about gas turbine engines, during World War II, a new type of airplane engine was developed in Germany and England. This engine was called a gas turbine engine. We sometimes call this engine a jet engine. Early gas turbine engines worked much like a rocket engine, creating hot exhaust gas which was passed through a nozzle to produce thrust. But unlike the rocket engine, which must carry its oxygen for combustion, the turbine engine gets its oxygen from the surrounding air. A turbine engine does not work in outer space because there's no surrounding air. For a gas turbine engine, the accelerated gas or working fluid is the jet exhaust. Most of the mass of the jet exhaust comes from the surrounding atmosphere. Most modern high speed passenger and military aircrafts are powered by gas turbine engines. Talking about ramjets, ramjet is a form of air breathing jet engine that uses the forward motion of the engine to produce thrust. Since it produces no thrust when stationary, it requires an assisted takeoff, like a rocket assist, to accelerate it to a speed where it begins to produce thrust. They work most efficiently at supersonic speeds around Mach 3, which is around 3,700 kilometer per hour, and can operate up to speeds of Mach 6, which is around 7,400 kilometer per hour. Now, talking about ideal properties of propellant. Next slide, please. One more. So, an ideal propellant should have high specific impulse. It should produce low molecular weight. It should be non-toxic, like gases. It should produce only non-toxic gases on combustion. It should burn at a slow and steady but predictable rate. It should possess low ignition delay, that is the time taken by propellant to catch fire in presence of the oxidant. It should have high density. The effectiveness of thrust chamber cooling should be high. It should be stable over a wide range of temperature. It should be non-corrosive and produce high temperatures on combustion. And cost and availability should be low. Now, Deepika will be continuing from here.
Hello, I'm Deepika. So, talking about specific impulse, it is a measure of how efficiently a reaction mass engine creates thrust. For engines whose reaction mass is only the fuel they carry, specific impulse is exactly proportional to the effective exhaust gas velocity. As you can see on the slide, there's a simple derivation of specific impulse. A propulsion system with higher specific impulse uses the mass of the propellant more efficiently. In case of a rocket, this means less propellant needed for a given delta V so that the vehicle attached to the engine can more efficiently gain altitude as well as velocity. In an atmospheric context, specific impulse can include the contribution to impulse provided by the mass of external air that is accelerated by the engine some or the other way. Can internal fan by the fuel combustion participation, then thrust expansion, or by some external propeller. Jet engines breathe external air for both combustion and bypass, and therefore they have a much higher specific impulse than the rocket engines. Specific impulse in terms of propellant mass spent has unit of distance per time with a notional velocity called the effective exhaust velocity. This is higher than the actual exhaust velocity because the mass of the combustion of air is not accounted for. Actual and effective exhaust velocity are same in rocket engines, but in practical they operate in air. So that's how the difference arises. One, also known as the rocket propellant one or refined propellant one, is highly refined form of kerosene, outwardly similar to jet fuel. It provides a lower specific impulse than liquid hydrogen, is more cheaper and is more stable at room temperature and presents a lower explosion hazard. RP1 is far denser than liquid hydrogen, given its higher energy density. It also has a fraction of the toxic carcinogenic effects of hydrazine, another room temperature liquid fuel. During the development of fuel, during immediately after the World War II, alcohols were commonly used as fuels for large liquid fuel rockets. Their high heat of vaporization kept regeneratively cooled engines from melting, especially considering that alcohols would typically contain several percent of water. But however, we recognize that hydrocarbon fuel did not increase the energy efficiency due to slightly higher density and but lack of oxygen molecule and negligible water content. Regardless of whatever hydrocarbon you use, it would also have to replace alcohol as a coolant. Many early rockets burned kerosene, but as burn times, combustion efficiencies, and combustion chamber pressures increased, energy masses decreased drastically, which led to unmanageable kerosene used as a coolant tends to dissociate and polymerize. Light bubbles causes cavitation and heavy ones passages in the engine. Yeah, lightweight products in the form of vacuum and cooling passages in the engine. The resulting coolant starvation raises the temperature further and causes more polymerization, which accelerates the breakdown. The cycle rapidly escalates until an engine wall rupture or other mechanical failure occurs, and it persists even when the entire coolant flow consists of kerosene. Mixed oxides of nitrogen, one of the missiles launched by India called the Vikas used this. The engine uses up to like 40 metric tons of UrHM as fuel and nitrogen tetroxide as oxidizer with maximum thrust of 725 kilonewton. An upgraded version of the engine has a chamber pressure of 58.5 bar as compared to 52.5 bar in the older version, and thus producing a thrust of around 800 kilonewton. And coming to the next slide, yeah, India has studied, produced, and used various strategic and tactical systems. Decades-long projects have realized development of all types of missile systems, including air, cruise, anti-ship, air defense, air-to-air, and anti-missile systems. India is one of the 7 countries in the world with ICBMs and one of the 4 countries with anti-ballistic missile systems. Since 2016, India has been a member of the Missile Technology Control Regime. The use of rockets for warfare in India has been recorded in as early as the 18th century. Mysorean rockets were the first iron-cased rockets in the world that were successfully deployed for military use. Mysore's conflict with East India Company exposed British to the technology leading to development of Congreve rockets and introduction of rocketry in Europe. Hence, rockets were first initially used in India. Research in missile technology resumed again after India's independence, along with the production of mass destruction weapons. Development of nuclear weapons was also followed by various missile programs in the 70s and the early 80s, with development of various ballistic cruise, surface to air, anti ballistic missile, and orbital launch systems. India conducted its first nuclear test and initiated with Project Devil as an attempt to reverse engineer Soviet surface to air missile FA2 guideline and Project Valiant to develop an intercontinental ballistic missile. In 2017, India produced self-defined empty self-defined missile technologies required to be integrated to produce most missile systems. And coming to the future of India and missiles and rockets, the technology is expected to become the basis of India's hypersonic missile and aircraft in future. India has developed an anti-radiation missile ARM that will help to destroy enemy advanced warning systems. And yeah, and that's all. That's all for the. Okay, this brings to the end of our PPT. Thank you.